welcome to the Charge Tape Lab. As a quick introduction, the purpose of this lab is to demonstrate electric force using home materials, in this case, charge tape. What are we trying to find? We're trying to find the charge on a piece of tape. The first fundamental principle we have is force diagrams, but more specifically, forces as vectors. When multiple forces are acting on an object, you can mathematically model it as vector equations and visually model it as so with arrows and magnitudes, these arrows representing direction and magnitudes, magnitudes, how big the force is. The second fundamental principle is Coulomb's law. Coulomb's law mathematically describes how point charges interact and the forces between them. As you can see, the force between 2 point charges increases with the inverse square of distance, this R term right here. This will be important later on. So the experimental design is that two pieces of charge tape modeled as if they're both single point charges, but in actuality the interactions are quite complex, as each electron in each piece of tape interacts with every other piece of electron in the other piece of tape. But these charged pieces of tape are brought together very closely. And they're charged by first interacting with a base tape, which is put on a surface, and the piece of tape to be charged will be put on top of it and then quickly ripped off. And just because of the material of the tape, this in effect charges it, giving it an excess or deficiency, as we will see later which one of those it is, of charge. And then one of these pieces is then suspended between two surfaces so that it forms a kind of bridge, this kind of bridge right here. So charged piece of tape A and charged piece of tape B are in a system with each other and the Earth. So if B is the piece of tape floating, the forces acting on B are the gravitational force from the Earth and the electric force upwards from the piece of tape A. And it's intuitive to see why these two pieces of tape would repel each other, because they were both charged in the same manner, which means that they would have the same charge, which means that they would repel each other. So my personal measurement is that my tape length was 21 centimeters, which with a 1 gram to 1 meter ratio is a 0.00021 kilograms. And the distance before floating between the two pieces of tape when I brought them together was 0.2 centimeters. So the quick calculation is that the gravitational force is 0.0021 newtons downwards. This was gotten by just multiplying the mass by the gravitational constant 9.81. And then we set the gravitational force equal to the electric force, and we solve for Q. And these two Q terms can be simplified into simply Q squared, because we're assuming that both pieces of tape have the same charge. And in my measurements, I got that Q is equal to 9.57 times 10 to the negative 10th coulombs, which when dividing by the charge of an electron is about 5.9 billion electrons that we find were in this interaction. The coding calculations were actually the same, just because the numbers used and the equations used were exactly the same, so line up perfectly. When I'm not perfect, the experimental flaws is improper measuring. My hand could have been shaken when I was measuring the distance between the two. I could have seen it wrong. And occasionally I had to touch the tape and mangle with the charge a little bit. And the air in the room, of course, could have moved the tape, changing the experimental numbers. And then there's a fundamental flaw in the mathematical logic, which is when we set Fg equal to Fe, that's a bit incorrect, because if Fg were to equal to Fe, the tape would not be accelerating, but because it's accelerating upwards, we actually know that Fe is going to be greater than Fg. But if we don't assume that Fg equals Fe, the math becomes much harder, so that's okay. So what if electrons had positive charge and protons had negative charge? It would have been the exact same. Positive and negative are just terms that humans use to understand the world around them. The interactions would have been exactly the same. And why should I touch the tape? Because everything wants to get to equilibrium. If I were to touch the tape, the excess charge in the tape would have just diffused into my body, and the tape would have just become more and more inert. So in conclusion, we found the charge of a tape by using known quantities of gravitational force and distance to solve for Q, using our fundamental principles of force as vectors and Coulomb's law. Thank you.